Hey there, Math 124 fans. Going to do third part of this Math 124 Exam 2 review. I'm going to talk about things that have to do with implicit differentiation in some way. First, a quick recap, and maybe we'll take an example. My favorite example to do is just to start with a circle. So let's say we have a circle, I don't know, of radius 3, and we want to take the derivative. Now, there's a couple ways to do that. The one kind of long way is to solve for y. If you just absolutely love to have y by itself, then you would do this. And then unfortunately, it leads to two different functions. One would be y equals the square root of 9 minus x squared, and one would y equals negative, the upper and lower semicircle. We say that these two functions are implicitly defined by this relationship. The original relationship is not a function. And so then you can take their derivatives. Now those derivatives are kind of messy. It involves a square root. So we can do that though. Let's move something around. I'll finish this exercise. Move this over here. So a calculus student would then write this way. This is not the best way to take the derivative and find slopes for a circle, in my opinion, which I'll talk about in just a second. But there's always some confusion about this. So you would do 1/2 9 minus x squared to the negative 1/2 times 2x. And that simplifies, if you want, to x over the square root of 9 minus x squared. That's fine. That's what you would do if y was positive, the upper half circle. If you did the lower half circle, it's going to look very similar. You're going to rewrite this as a half. Let's just skip to the point here. Negative 1/2 9 minus, this is x squared, sorry, x squared to the negative 1/2 times negative 2x. And this should have been negative. Ooh, I'm making mistakes left and right. This is going to be 2, not 2x, it's x. This is what I get for 3. We'll do some problems here where I'll try not to make mistakes. They're not quite the same. One of them has a positive, one of them has a negative. It appears that when it's the negative, you get a positive, and when it's the positive, you get a negative. So it seems to flip our signs. There is a way to do both those at the same time. And this is the idea of implicit differentiation. We say, let's pretend we have a function here. Maybe it's f of x, maybe it's g of x. I don't know. Could be f of x, could be g of x, could be something else implicitly defined by this. And then let's differentiate with respect to x. Well, we know how to differentiate with respect to x. This becomes 2x. You'd have to use the chain rule here. F of x to the 1 times it to the inside. And that's the part we don't know, so let's just write f prime equals 0. And then we solve for f prime. But it turns out whether it's f or g doesn't matter. So instead we just leave it as a y, and we call this y prime, or dy dx. And that's the key maneuver. Now, when I was a student, I remember just saying, okay, you're saying every time I take the derivative of something with y, I write dy dx next to it? Essentially, yes, but I want you to understand why. Okay, so let's solve for dy dx. So then we get 2y times dy dx is negative 2x, and then I get dy dx is negative x over y. And that is one rule to rule them all. So why does that work? Well, because it works in either case. If this is your y, and you can look at it, if this was my y, and I plugged it in here, do I get this same rule? I do, because the negative and negative makes it positive. If this is my y and I plug it in, I do. If you don't mind having a y on this side, then you would just leave it like this. It's way better. Okay, so that's the idea of implicit differentiation, is that you don't have to get y by itself, which is a huge thing. Makes our lives much easier. So you don't want to be scared of this method. You want to embrace it. It makes things better. Okay, so we can apply this to a few situations, inverses and many other things. But one of them is logarithmic differentiation. So we say the reason this looks messy is because there's an x here and there's an x here, and there's a way to get rid of it. Just take a log of both sides. Then we can use that log rule, that log of a to the b is b log of a. That's by far the most important log rule. So this becomes cosine of pi x. There's other ways I've seen people do this, but it doesn't matter. At this moment, we've gotten rid of that problem. Now we're going to differentiate with respect to x. And here's where the implicit differentiation comes in, because we're not scared to have that y there. We just write 1 over y times dy dx. Then the rest of this is the product rule. First times derivative of the second plus second times derivative of the first. 2 over 2x plus 1. That 2 came from the chain rule. Plus, now the derivative of the first would be minus sine. Loveless law of the c's. If it starts with the c, the derivative is negative. Negative pi sine of pi x log of 2x plus 1. Now, honestly, in a question that says find the value at 1, I am not inclined to simplify because I know I'm trying to find the equation of the tangent line at 1. And so I don't really need to simplify anything. I just need to know those two things, which is what is the y value at 1 and what is the slope at 1. So honestly, what I would do is I would just plug a 1 into the original thing to get the y value. So that's going to be 3 to the cosine of pi, so 3 to the negative 1. So this is going to be 1/3. And then I would plug a 1/3 in here, and I would plug a 1 in here. So that's just kind of experience of, if I know I'm just computing a value, I'm not going to spend a whole bunch of time. So this is going to be 1 over 1/3, which is 3 dy dx. This becomes negative 1. You need to get really good at knowing these values if you're going to continue on in these courses and be successful. There's plugging in a 1 there. This is going to be a pi. When I plug in a 1, oh, it's just 0. And so I get negative 2/9. Yes, it matches my solutions. Okay. I don't know. Do we need to see another one? I know that that's not very easy to see. For some reason, sometimes when I do a screenshot, it doesn't look as good as other times. I probably should investigate how to do it nicer, but here you go. I want to get through this one. Cosine of 4x, the derivative of this is 2x over x squared. So really good to know your product rules and all those things well. Negative 4, this is very similar. 4x, this is just random old exam questions I found. If it does ask me for dy dx, then I'd multiply both sides by y. So mess times y. If I wanted to go further, I could replace y with this. All right, being very lazy there. So now let's get to something that truly is implicit. What do I want to do first? Let's just grab one of these. Look at this weird thing. We want to find this point where the slope is 0. So we want to find when dy dx is 0. This y squared, I guess I should read the question. I was just assuming based off of the picture. Find the x coordinate. Okay, we are finding that. So I really would like to take the derivative with respect to x. And these are the sort of situations implicit differentiation works so well. I mean, there's really nothing else to be done. So there's the derivative of the square. Eventually I'll do e to the y dy dx equals 0. So I'm just taking the derivative of each of the terms. Now this one requires a little more work because I need the derivative of the inside. Derivative of the inside is 3x squared minus 2y dy dx. Now you may wonder that last term is often a place people make an error on, but the derivative of this one is, again, you're thinking of it as a function trapped inside of a square. So it's going to be 2 blah to the 1. You'll leave the inside alone. Then you do the derivative of the inside. That's what I did here. Now, there's a maneuver here. The goal is to find when dy dx is 0. So the goal is to find when this is 0 and this is 0. So if I was doing this, I would not try to simplify and find dy dx. I would just replace those with 0 and solve. So then I get x cubed minus this squared. That's 0. That's 0. So all you have is 3x squared equals 0, which is awful nice. And that leads to only two possibilities. Either 3x squared is 0 or x cubed minus y squared is 0. So either x is 0, which is not the case because that's not the one in my picture. That would have been this one or this one. I want to know when this is happening. So we keep going. So I need x cubed equals y squared. And at this point this often happens in these problems, is you get to some condition where you're like, my variables aren't going away. And that's where you need to remember that this point you're trying to find, this xy point. Yes, I know the slope is 0, but I know something else about it, which is it's on the curve. So both of these things have to be true. Now, why would that be helpful? And you can see why I paused there. Really, the moment I wrote this, I was like, what am I going to do next? And then I saw, oh yeah, I know this as well. So in fact, it might have been better for me to leave it this way because I know that this is 0 at the point I'm trying to figure out. So 0 squared. And that's nice because that leaves just a y. So y is the log of 4. So that's kind of fun. That's the log of 4. Do I have to find x too? Oh, I guess it's not bad because I have this relationship. If that's the log of 4, x is the log of 4 to the 2/3. Done. So that was kind of interesting. Well, I don't have my solutions for that one up and ready. I think I'll stop at that. I think we've given a good enough taste of implicit in those few problems. Hope that's of interest. Again, you can always find more practice problems on my materials page. I think I talk implicit in this review. Yeah. Talk about where it comes from. I talk about how to use it. You can also always look at my lecture materials. I have old lecture notes. Those are going to be a good place just for basic study. If you need practice with parametric, you need practice with, that's more parametric. Implicit, I talk about implicit. Plenty of places to practice. I always tell students, your job, oh, that's one I did in my notes there. You need to figure out where your issues are. Part of your studying should be that, not just trying to sort of blindly go through old tests. You should scan through old exams and ask yourself, where am I stuck? What do I need more work on? Then go seek that out and ask about that. All right, I hope this is helping with that.